to be here. And yeah, and this is my talk title. Good. This is a very fun topic and for lots of reasons. And let's see if there we go. Okay, so it's a problem. It's sort of a modern bit of research that's going on now, but it sort of points back to things from the early 40s, which is sort of always really cool to do. So here's just some notation here. Firstly, a lot of what I'm talking about is joint with a student who worked with me. He's graduated now, Ed Floyd, non-academic job, a little sad, but oh well. So groups. Groups are all going to be P groups in this talk, finite P groups. If a cyclic group comes up, it will be written like that. Cyclic group of order P to the K. Okay. If I talk about finite G spaces, what do I mean? How about something like this? A space whose localization at P is a retract of the P localization of a finite GCW complet. Okay. I got that one right. Spectra, finite G-spectra, so compact objects in the mode of G-spectra. So these are just spectra of the form. It's, you take the equivariant suspension spectrum of the sort of thing I just mentioned, and then maybe desuspend it by a representation sphere. So, so these things come up a lot in the Balmer spectrum, equivariant, stable homotopy and things like that. In notation, most of the time I'm going to be working with spaces, and we're just going to be talking about good old classic. You can visualize it, the fixed point space, and the associated geometric fixed point space of spectra is usually written with that, something like that. And I misspelled something as well. So here's the problem. How is the homology of a fixed point space related to the homology of the space you started with if you have a G action? So this has a famous old history. It is one of the first things in math that was taught as sort of traditional subject when I was in graduate school. Can you see? I'm so hide behind there. Okay. Okay, so here is two classic theorems. Okay. So a space is mod P acyclic if it's homology, mod P homology is homology of a point. And this is a famous theorem by P.A. Smith, 1941. Perhaps there's some references that you could deduce it from by him in the 30s. So it's really old. Let X be a finite CP space. If it's mod P acyclic, so are its fixed points. Okay, so this is very famous theorem. So this got an upgrade about 10 years later by Ed Floyd. This whole project made me really happy because I was a colleague of Ed Floyd for my first few years in Virginia, and the topologists there, Connor and Floyd, were so responsible for a lot of this work, equivariant work, as well as cobordism work, and all that's relevant here. Anyway, this is the upgrade. That if you have a finite CP space, then the amount of the total dimension of the mod P homology of X would be this bigger than the homology of the fixed point set. And so, you know, you're learning something about every CP space. Right? It's like better, right? And perhaps you could almost have seen this in the older work, but anyway. Okay, so they actually, I should mention this because I think there's some questions here in our chromatic versions that are still not so clear. They actually prove these under the condition that X is just finite dimensional. So for instance, people who are quite interested on the actions of finite groups on Euclidean space, for instance, which is mod P acyclic, for instance. So you can use these theorems to deduce things about other groups. That was just for CP, right? So, you know, if fixed points are connected in this way, if you have a normal subgroup, you can do it in two stages, take fixed points. And so P groups are solvable, and so you can deduce stronger versions of both theorems. And so suppose you have any finite G space, and G is acting on it, and G is a P group, and H is a subgroup. I'm giving you the most general version of that, because that's going to be more relevant to what I want to do later. So Smith's theorem implies that if the H fixed points are mod P acyclic, then the G fixed points are mod P acyclic, because you can sort of climb your way up by, right, H would be inside it, would be a normal subgroup of something of, you know, it'd be index P in a bigger group and so on, and so you could climb your way up from there to the whole thing. So this is, you don't normally see this stated, but this is a consequence. And Floyd's theorem says the same sort of thing, but about dimensions, okay? So these are going to be the sort of theorems we're going to be looking at generalizations of later. And, okay. So here's an example, if you've never thought about such things. Well, here's an action of C2 on R3, just let it be reflection through the XY plane. And so this gives you a CP action on the space of lines in R3. And the fixed points are, well, let's see, lines that don't get moved. So I guess you have the North Pole, South Pole line, and then you have anything that was in the XY plane. So it's giving you the lines in the plane and the lines, well, okay. I wrote it in a way that suggests how you would think about this normally. It's, anyway, it's S1 disjoint union of point, okay? So let's see how Floyd's theorems work. So Floyd's theorem says, well, the homology of the left side should be greater than or equal to the homology of the right side. And what do we get? We get 3, yes, okay. So it's close call, right? Close call, okay. So anyway, so how about other field coefficients? So let's look at characteristic 0. Well, the left side is acyclic, right? And the right side is not. So that's interesting, you know, a little interesting. So being Q acyclic does not imply that the fixed points are acyclic. Okay. So anyway, this actually represents a lot of the theory, this stupid example. Yeah. In fact, I sort of started getting into this project when I was thinking about something like this in like an undergraduate geometry class I was teaching. I wasn't using this language. But okay, so here are 2 recent papers. Balmer and Sanders have this paper where they are looking at the Balmer spectrum for equivariant stable homotopy theory of a finite group, and they identify these tensor triangulated ideals, and basically the answer is you take geometric fixed points, the subgroup, and then you look at all the spectra, the finite spectra that are acyclic in one of the Morava K-theories, and that gives you some obviously tensor triangulated ideals, and they sort of show that this is the answer. And then, yeah, maybe I should say just what I said, yeah, okay. So this first paper, they figure out what these ideals are. They also do all the work to reduce questions that one has down to the P group case. So you can just forget about non-P group because you can answer all questions. If you can answer the P group situation, you can answer it's just group theory after that to get any questions you might have about the composite order groups. So they do all this stuff. And so you're really left focusing on the P group situation. And you're left looking at the topology of these tensor triangulate, of the spectrum. And it has to do with which of these ideals are contained in other ideals. And they say a little bit, which I'll say a little bit more about. And then there's this 6-author paper, a very long list of names, that identifies this when G is an abelian group or abelian P group is maybe. And so understanding this topology turns out to be equivalent to statements that look just sort of like Smith's old theorem, which is rather cool. Yeah. So let me just remind you, this is, I mean, probably everyone knows this, but just and some notation as well. So the Morava K-theories are the theories that are going to play the role of mod P homology. So that's sort of the idea that there's some actual good theorems out there if you don't just use mod P homology. So these things, they're complex oriented, they have good theory of Turing classes, and there's a formal group associated to complex oriented theory that from group type N. They're localized to P, by the way. The K0 is just, maybe you define it as a rational homology. And for the other ones, this is the coefficient ring. The real point here is it's a graded field, okay? And this invertible element is sort of like a little like dot periodism type stuff, right? So, and sometimes it's useful to like K infinity DHCP. Okay, so here's notation I want to use. I'm going to be talking about the dimensions of things fairly often, so here's just some notation for it. So I said the coefficients are a field, and it follows that Kn of anything is a vector space, graded vector space over the graded field, so you can talk about dimension, how many generators you need. And it also pretty much implies you have a very good Kuhn theorem as well, if you haven't thought much about these theories. So so that's also really handy for calculations. So these are famously the fields of our subject. So here's something a lot of people know. Doug Ravenel showed that if you have a finite spectrum or space, whatever, then if it's acyclic in one of these theories, it's acyclic in the previous ones as well. So that's interesting. Now, a lot of people, and this includes me until just a couple of years ago, don't really notice that he proves something else that's even stronger. He shows that the dimension is going down as you pass from one to the next. So that's sort of a nice thing to know, which if you look, this is all of his famous Conjectures paper. It's somewhere in the early sections when he's proving theorems, not just conjecturing things. It's in there. So here are two new theorems. So now we have the versions of Smith and Floyd's theorems that are new. So the sixth author, I'm jumping to what the sixth author paper did. They show if you have a cyclic, if you have a cyclic, a cyclic group a cyclic P group acting on X, and they're doing it on the spectrum, but you can translate it to this very easily. If it's Kn plus 1 acyclic, then the fixed point set slides down by 1, it shifts down by 1, and it will be Kn acyclic. So, and the first paper by Balmer and Sanders proved this just when K equals 1. So it was sort of quite interesting that they...
N equals 1.
What? K equals 1. K equals 1, because they prove it for just a cyclic of the order P. Okay? And yeah, so this actually, the fact that they proved this theorem really changed one's guesses about what was happening. And we're able, Chris and I are able to show this stronger version, okay, under the same hypothesis. So we'll be explaining these things a little bit. So yeah, I'm sticking a little bit of technical bits of proof so you can see some of the ideas here. And most of them, I mean, my contribution is the second business here, but it has made me think hard about the first thing. And if you read their paper, it's a little dense reading. I'll say this. Probably the authors would agree with me when they also are doing it for a general abelian P group, which we'll see for certain purposes it's not necessary. But anyway, so I've been thinking hard for a little while about I wanted to understand the proof itself, and I came up with something. But then we have this wonderful postdoc now at Virginia, William Valderrama, and I've been chatting with him, and he keeps handing me these little things like a short proof, a really short proof, a really, really, really short proof. Anyway, so I just have one page where it's just sketching the ideas. So the nice thing is you can sort of sketch the logic in the same way that people proved the original Smith theorem, not P.A. Smith's proof, but sort of more modern versions, like if you read in Tom Beek's transformation book, for instance. And so suppose you're assuming your space is acyclic in your theory, and so you can put that in the EC crossover CX slot, and you can deduce so that says a map to a point is an isomorphism. So you get, and you hit it with sort of the equivariant, the sort of cheapest equivariant theory you can think of, EC cross C blank, and it gives you a map from from the homology, cohomology, BC up to the other one. And this will be an isomorphism, and so I've switched to Morava EN theory. So it's, anyway, this is a pretty easy thing to see. So this doesn't use very much about it's Morava E theory. So anyway, you switched over to there. And then you do something that is done in these modern proofs of classic Smith theory, which is you localize. One of the points about these complex-oriented theories is you can calculate a complex-oriented theory on the classifying space of a cyclic group has this nice description in terms of formal group law theory. And so you invert an Euler class. There's an obvious Euler class in the that's associated to the obvious bundle of the cyclic group, line bundle that becomes trivial when restricted to any subgroup. And so this is classic stuff. So you get localization. You have the map from the EC cross CX to BC cross XC, and that will become an isomorphism after you localize certain classes. So you do that, and so we get something like this. And let's assume the left-hand side is non-zero, because it would have been bad if we had killed everything off. And so already, if you assume the left-hand side is non-zero, which I guess is a calculation of some sort, you already can conclude that the fixed points are not empty. So we could be back in the base set. What's a base G space? It's one with a fixed point, a G fixed point sort of name. Okay, so to this point, and now this is my quick sketch proof. This isn't the whole, right? I don't expect you to totally take this in, but the point is it's not that scary. And then you just get in there, and you have to mess a little bit with what P-series looks like or something in formal group law stuff. And you can see that you've roughly inverted Vn by inverting this class, and then you're sort of in the height end situation, and you have this last thing. So that's a sketch of the proof. So it's not that bad. You can make most of the proof look rather like traditional stuff, and a little bit of formal group law stuff. Well, you had to use something about formal group law, so it's pretty minimal. Okay, that's the end of that. So it's not too scary. I was scared by the proof in the 6 author paper, so I wanted to prove that it didn't have me scared. Okay, so again, you can iterate these things, but it's sort of a little funny when you iterate them. Okay, we learned a theorem about cyclic groups. Okay, not just mod P groups, right? So here's a definition. Given, and since we have some proof theory people, you'd be excited by this. You're given a subgroup H inside G. Here's a number you can assign. What's the smallest number of steps to climb yourself from H to G, where each subquotient is a cyclic group? Okay. So if G is abelian, it's just the rank G mod H. It's a really weird function in general, which we discovered, Chris and I, by just searching for weird examples. So maybe I'll say something about that later. But anyway, there we are. So here's what you get by iterating the theorem I gave you, just like I iterated the Smith theorem at the beginning. The 6 author paper, the Chromatic Smith theorem, tells you if R is bigger than this number, then and you have a finite G space, and it's acyclic in n plus r Morava K-theory, then the fixed points are acyclic in the nth Morava K-theory. This is the sort of thing you learn by iterating. So you have this sort of shift now. So this is the new aspect of all this stuff. It's like not just one theory, it's 2 theories playing off each other. And then our theorem gives the same thing for just counting dimensions. Okay? So this is what you learn from this stuff. So that's sort of fun. Okay, so here's 2 general problems. And this ends up being equivalent to the questions that are about the topology of the Balmer spectrum. For what n and m, is it true that if your theory is if the H fixed points are acyclic in one theory, the G fixed points are acyclic in in the other theory, okay? And let's see, so, okay, so here there's just a name made up, okay? So if you have an M and an N and a G and an H, which this is all holding for, we'll say the Smith theorem holds, okay? And then the same thing with the Floyd thing. When is it true that for all G spaces X, the dimension of the nth Morava K-theory of the H fixed points is greater than or equal to the dimension of the nth Morava K-theory on the G fixed points, okay? A little crazy. And again, we say the Floyd theorem holds, okay? So here is something that's pretty obvious. I guess if the Floyd theorem holds, then the Smith theorem holds, okay? So this is our key observation in all of the work I've done, which is the converse holds. If you just know, if somebody just tells you, oh, I know somehow, because I'm clever, that the GH&M Smith theorem holds, then you can deduce this fact about dimensions. So that's sort of neat. It even works when N and M are infinity. So this could have been, this proof gives a new proof that the P.A. Smith's theorem implies Ed Floyd's theorem also, rather, anyway. So here's what we really do. So this is sort of cool. Prove the contrapositive, okay, and in a more precise form. It's also convenient, as we'll see, maybe to work in the stable world. I don't really need to, but it's a little easier to say things. So here it is. Suppose you have a finite G spectrum, and so we're trying to show the contrapositive. So you have something showing that this chromatic Floyd theorem fails, meaning the H fixed point, the size of the mth Morava K-theory of the H fixed points is smaller than the nth size of the nth Morava K-theory of the G fixed points. So that's saying we have a counterexample. Then we want to find a counterexample to the Smith theorem, and this more precise version tells you how to find it. There's some number d, and we'll see what this is about, and an equivariant stable retract of the deep smash product of x. So we're going to take x, we're going to smash it with it a bunch of times, and we're going to split a piece of that off of it. It'll still be a G thing, a G spectrum, and this guy will have the property that the mth, it's acyclic in the mth Morava K-theory, and it's not acyclic. The G fixed points are not acyclic in the nth Morava K-theory. So that's going, yeah, and D basically, essentially depends on M, and on the size of the one of those guys, and it can be very big. Yeah, pretty big means really pretty big. Yeah. It might be something like 2 to the yeah. Something, choose something where the top number is a large power of 2 or something like, anyway, so anyway, it's large, yeah, big, yeah, anyway. But, so what? Okay, so here's a sketch proof, okay, the key observation. So, first of all, this is I'm recycling an idea used by Jeff Smith in the 1980s. It's sometimes it's helpful to be an older guy and to remember this stuff, especially since he never really wrote it up. And it's sort of part of the story with the nilpotence theorems. Everybody remembers what the nilpotence theorems and then the periodicity theorems say, but people tend to not think about the details of proof. Well, this is one of the details in the proof, was this idea that Jeff Smith had. And it's sort of written up in Appendix C of Ravenel's Orange Book. Okay, so the symmetric group at border D acts on anything that you tensor with itself a bunch of times in a symmetric little category or something. Anyway, here we have acts on the G spectrum, and one of the reasons I'm working in the stable world is so I can. That's an additive category, so it extends to an action of the group ring. So the group ring acts up the homotopy on X smashed to itself to B. Okay, and this is in the category of G spectra. Okay, so if you have an idempotent in a group ring, and it's acting like this, you can, it breaks a piece. You know, idempotents are basically, the point of an idempotent is to write something as em plus 1 minus em, to break into pieces. And so the same thing happens in topology. I mean, you can take the mapping cone, the mapping telescope of EM itself, or you can define that thing by Brown representability or any way you want. Yeah.
So you're not claiming here that this smashed power is a ZE module, right?
We're working in the category of the homotopy category of equivariant, of equivariant homotopy. So this action, you know, we just need that there's this object called X smashed to the D, that's a G spectrum, and it's, Okay, so we're working P local category, so we can sort of extend this action of the group to the action of the group ring. Okay. By the way, if you wanted to work with spaces, although nobody here does, except me, you could suspend once or twice and it would be good enough. It's still not, you wouldn't quite have an action. I mean, it's still not, you know, you can add maps at least then and still get the results. But anyway, we have this thing. So this is a way to break something off. You can just smash something 3 times, choose an idempotent and symmetric group on 3 letters, and it'll break into pieces. So that's, again, what idempotents are good for. Okay, so this is the form that my thing's going to take. So just to make it, let us think about sort of linear algebra and representation theory. Let W be this vector space over this one field, Km, and let V be this vector space over this other field. But they're both vector spaces over these, you know, nth graded, all this junk of graded vector spaces over graded fields. And our assumption was that the dimension of W as a vector space over Km was less than the dimension of V as a vector space over Km. Okay, so W is smaller. I mean, it doesn't really make sense because they're over different fields, but that's what I mean. Okay, so just keep that in mind, just sort of intuitively, right? That one is smaller than the other. So if you have something of the form I just mentioned, you have a Kuhn theorem, and so Km of the fixed, so taking fixed points is symmetric monoidal, right? Or it commutes with smash products. Okay, taking geometric fixed points, and also Morava K-theory satisfies a Kuhn theorem, and so that tells me that the E will just pull out of all the symbols. And so if you wanted to know how big, what is the nth Morava K-theory of this piece of X smashed to the D, it'd be E, this idempotent E acting on this vector space, which is tensored, that's obviously the first W is tensored over the field that you relate, that's involved, which is the Km star, and the other one is tensored over Km star, right? So they're tensoring over different fields, but they both have this form. You have a vector space, you tensor it a bunch of times, and then you hit it with an idempotent, okay? By the way, some of you may know at the prime 2, the Kuhn theorem is a little screwed up. Like I know it likes this, right? It's this exotic structure. We're just talking about dimensions, and it doesn't, you can filter that probable way. So we did think about that. So we have these sort, what's our goal here? Our goal, we were assuming W is smaller than B. We would like to choose a D and an E such that the EW tensor with itself D times would be 0, but the other guy would be non-zero. So now, okay, we're talking about the symmetric groups of acting on vector spaces. You know, there are a lot of people who've thought about this for a long, long time. This is some of the oldest math out there in the world. And so there's known stuff, right? And so one thing people do is they look in characteristic 0. If you have a partition of a number called D, and you partition it and you draw these little Young diagrams, because it's sort of a fun thing to do, and you can ask this question. There's an actual formula you can write down for an idempotent. And then people have figured out if you have a vector space and tensor it D times exactly when it's 0. Now, actually, we found out 2 weeks ago. I was at MIT and I was talking to Pavel et.al. et al. About something else that I was curious about. And he actually told me, oh gosh, I shouldn't hit my button. Okay, I'll put that back in a second. I was wondering, I was assuming somebody worked out for graded vector spaces when something is zero, because standard books just have a vector space, and then it's is that the Schur functor or the Weil functor? Which functor is it when you do this? The vector spaces. This is going from vector spaces to, anyway, it's a functor of a vector space is constructed from a module, from a symmetric, from something with a symmetric group. So this is this classic Schur duality, is that what it's known as? Anyway, whatever. Equivalence. So anyway, so basically, you know, if you do something like this to a vector space, if the vector space is bigger, it's going to be bigger. And if the vector space is really big, it's definitely got to be non-zero. And if it's really small, maybe it will be zero. So think, for example, like exterior powers as a functor of V, right? It vanishes on small vector spaces, and then it turns on, right? So that's what these things are. So somebody figured out when it turns on, okay? And so for small vector spaces, so this idempotence is in the rationals, but every so often you're lucky, and it actually has the denominator involves something called hook length. But anyway, the denominator involves, it doesn't involve having to divide by p. And at the prime 2, these are the partitions that look triangular. Those are the only ones that are odd primes. There are a whole bunch of them. Anyway, so if you're looking at Doug Ravenel's book, he never uses this word p-core, but he tells you some examples, and they are p-cores. So in that case, you would have a result. You could sort of move this characteristic 0 result to characteristic p, right? Because this action is just taking a basis and permuting things around. So the same result will hold there. So now one can check that given any graded vector space W, that there is, and something whose total dimension is bigger, called V, that you can choose a p-core partition of some D, and the D tends to be a fairly substantial number, and such that W is small with respect to this partition and V isn't, and so you let that be that and you're done. That's how you do it. Okay, so basically you're tensoring. You have this vector space W. You tensor it a lot of times, and V. You have this vector space. You tensor it a lot of times, and the one is smaller than the other. So you figure it's getting, it keeps happening when you tensor them together, and then you're breaking off pieces, and you have more and more pieces as you tensor more and more. And sooner or later, there's a guy that's 0 over there and not 0 over there. Why not? I mean, something had to be going on, right? So that's the sketch proof of our key thing. So let's have some fun with it. Okay. So first of all, back to this chromatic Smith problem. So this is this general problem that's equivalent to the topology, the Balmer spectrum for equivariant stable spectra. This is the general problem. Okay. So you have this thing. So one's searching for blue shift numbers. So let me define this. So if you have H's inside G and you fix N, let this RNGH guy be the smallest R. I mean, this is organized for reasons, so we'll make it fit nicely later. So I'm sort of letting the M above to be called N plus R. Why not? Okay, the smallest R, right? So notice if I had a bigger R, remember, if it's acyclic in one theory, it's acyclic in the previous theory. So this is why you can do that using Ravenel's old result. So we have this question. So find the minimal R such that this property holds. A little odd, but that's what we're just looking for. Okay. So translated to Balmer spectrum language, the guy on the left is in one of these tensor triangulated ideals, and the guy on the right is defining a different tensor triangulated ideal. So you're wondering when one is contained in the other. Okay, but that's the problem. Okay, so that 6-author paper for cyclic groups. Remember, I gave you this funny number RGH. It was this sort of generalization of rank, where you sort of climbed up from H to G by biggest cyclic groups you could. So that's what the theory, this is just translating this. The blue shift number is less than this number, which is just something that involves the groups G and H, okay? So I'm just going to throw this out there. I don't know if it's really true or not. Well, okay, it's good. Okay, so the blue shift conjecture, this is right, okay? So the sort of proof I gave you of what they did when you try and think of generalizing it, you think, gosh, we are just so stuck with Chern classes and stuff like this, and I'm not going to do anything with abelian group except with abelian groups. And so from that point of view, you can't imagine improving their result. So in that case, this has to be right? Okay, so there's a conjecture. Okay, so it includes the conjecture that it's independent of n, which doesn't have any conceptual reason why that should be true. Okay?
So just to be clear, you said it's true when G is abelian.
Well, yeah, we'll see. Yeah, we'll see when it's true. Yeah, it's true. Yeah. So right. So that's right. We'll see. We'll see exactly. I'll talk about that. So we know that this is true. Okay. So let's say you wanted to show RGH was exactly right. You need to find examples, right? You have to find, with R being a smaller number, let's say, subtract 1 from that, you need to somehow out there find a G space X such that the H fixed points are acyclic in Kn plus R, and the G fixed points is not acyclic, right? So we're doing it that. So you want to find these counterexamples, okay? So it's hard, okay? So the 6th author paper, they find in the literature, in a paper of Gregorone and Catherine Lesch, they find something that lets them to show that they're basically focused on the elementary abelian groups, CP to the D, and the trivial group is the second one, and they're able to find that they have this example, and it lets them deduce this. Okay. The example of Aron and Lesch is rather related to the very old example of Steve Mitchell, which was the first example of type N space, you know this stuff, and he was using also idempotents coming from group ring actions, and it's all sort of jumbled together. Okay, it was not so, anyway, it probably inspired Jeff Smith the way he did. And we've sort of seen how if you know some of these things, you can deduce other things like pulling back actions and things like this. And let's just say you can deduce this. And so this is the punchline of the 6 author papers. We can do this, or we get definitive answers for that the blue shift numbers, prove the conjecture, right? When G is abelian and this number I defined RGH is just the rank of R mod H. Okay, so so they get their upper bound from their general theory, which involved the localization thing, and then they get their lower bound by finding an example. Okay, whoops. So it's hard to find examples because I mean it's not even easy to just find example. You know, when I say a finite G space and XH is acyclic in some theory, it means it has some type, and you just don't find like a type 23 space sitting out there that's in front of you, right? I mean, if you've ever thought about this stuff, right? They just aren't around. Like, for instance, yeah, right, exactly. Right. So for example, manifolds are always type 0 or type 1, so you don't get very far into manifolds. It's always anyway. So it's already a little scary because it's hard to explain this to anybody who's not an algebraic topologist. Why do I care about this? Anyway, it's like dark matter, right? You know, it's all over there, but you know you can't see it. Okay, so anyway, the equivalence of the Smith theorems and the Floyd theorems give you a much easier way to do it. Okay, so much easier to find lower bounds. All you have to do is, if you want to show this shift number is at least as big is bigger than some number R, you just have to go and find any old G space such that the n plus R, there's more n plus R Morava K-theory than H, well, there's less, yeah, anyway, what I say, Kn plus R, the dimension of the n plus R K-theory of the H fixed points is less than that. And this turns out to be much easier to do. Okay, so when P was 2, Chris Lloyd and I studied G spaces of the form, just take a real representation of G, okay? And this is like my example I gave at the beginning of the talk, just take the lines through, in that, so the projective space associated with that. So this is giving you something that non-equivariantly is a real projective space, I guess, of one dimension less than the dimension of B. And then it has a G action, and it's pretty easy to figure out the fixed points for any subgroup. It's sort of called eigenvalues and eigenvectors or something like that, or any P-typical. Anyway, it's representation theory that you learned, or you should have learned in graduate school. And then the Morava K-theories of projective spaces ends up being really easy to compute, because the first differential is given by the Steiner operation, Qn, which is really easy to compute, and you can just crank out the numbers. You can crank out the sizes very mechanically. And again, if something is, it's very easy. And so I was messing around by hand with some examples and could redo the lower bounds that these guys had by hand with this, and also at odd primes. But then we were looking for some of the first cases that couldn't be handled by the 6-offs, and every time, we talked to Chris about this, he'd come back the next day, he had programmed everything we talked about into little programs that got better and better. And, you can pull out from representation theory stuff, you can pull out all this information about what are the irreducibles and good stuff like that. So he was just searching randomly for a while until, he suddenly surprised me. And so we eventually, he found a couple of examples. He found a few examples. Now some were deducible from other examples. We found a couple new examples, and then sort of tried to figure out what we were looking at. And it turned out the new examples were all the extra special two groups of, I guess it's called positive type, a little plus. Is that right? Something anyway. Which couldn't be quite gotten at by the other guys. So we improved the bound, the lower bound. We improved the lower bound by 1, which is not a lot, but it's more than 0. And let me just show you the very first example. So the first new result, this is what couldn't be done by the 6-off figures. If you had just a dihedral group of order 8, and it has various elements of order 2 in there, but some of the elements of order 2 are not central. So take that particular subgroup, okay, in the dihedral group. And the upper bound, this R guy I mentioned, is 2, and the lower bound coming from pulling back by quotienting down to the elementary abelian situation gave you just 1. So there was, the question was it 1 or 2? Was this, and so we just have to find an example. So here's what it is for, in general, the representation that witnesses this, the V is, you have 4 one-dimensional representations, and you take a whole lot of copies of each one, and 1 copy of this 1 extra 2-dimensional representation. So let me just say what happened when n equals 0, okay? When n equals 0, you have 4 one-dimensional representations, and you take 2 copies of each. So this is taking the dihedral group and modding out by the center. It's a C2 cross C2. So you have 4 different projections onto C2 there. Oh, well, 4 ways of getting, 4 one-dimensional representations there. And then you also have a 2-dimensional irreducible, okay? So this is 10-dimensional, I guess. And so RPV is RP9, okay? So we have an action of the dihedral group on RP9, okay? And its D8 fixed points would be all the one-dimensional sub-representations. That's why it's easy to do these things, right? You think, what's a fix? Well, I guess this line has to be fixed. Well, that meant it was a sub-representation, right? And so that line has to be in one of those first 4 spaces up there. So it's a line in R2 in 4 different ways. So that's 4 copies of RP1. And the tau doesn't really enter the picture here. And so K0 is rational homology, so RP1 is known as the circle, so its rational homology is 0 in dimension 1, and 0 in 1, Q in dimension 0 and 1, so it's 2, so 8. 4 times 8, that's the size of the rational homology of 4 copies. This is all unreduced. Okay, so now how about that? So now we restrict to that subgroup, and the four little piles of 2s sort of dump themselves into making 2 piles of 4. And then, so now we're looking at a group of order 2, so it has 2 representations. I call them sigma 1 and sigma 2, but they're also known as the trivial and the sign representation. Right? And tau, when you restrict it, becomes a copy of the regular representation. So you have 5 copies of each of these guys. So what does that mean? It means the fixed points are 2 copies of RP4. So what's cool about RP4? We're looking at K1. That's so RP4, K1, it's really the mod 2 K-theory. The first differential in the Atiyah-Hertzberg spectral sequence what's called Q1, the Milnor operator in Q1. It's square 2 square 1 plus square 1 plus square 2. And so that's going to take the one-dimensional class in RP4 up to the 4-dimensional class. So that differential is going to knock out 2 dimensions. So the mod 2 homology of RP4 is 5-dimensional, but when I take its, this differential gets rid of 2 dimensions. So the total size here is just 3, as 2 times 3 is 6. And you may notice 6 is less than 8. And so we just proved that this blue shift number is 2, not 1. Okay, so that's pretty easy. That you can see you could program this to hunt for things. If you didn't see the patterns yet, after a while we did notice. So we did, obviously we're able to do something like this. So by the way, some of you know a little bit about the extra special 2 groups. They always have a whole ton of one-dimensional representations, and then they have this one exciting extra representation, and it's when you restrict it to sort of a maximal elementary 2 group that does not contain this, that does not intersect the center, it's sort of 1 copy of the representation there. So we have this story holds in general. You have these little I think of them as little piles of representations, and then you have this one extra guy. When you restrict to it, you drop one more thing on top of each one, and it lets some differential knock things down, and so you win. So it's sort of delicate because you don't win by a lot. So in other words, we haven't been able to improve the blue shift, but I don't think the blue shift, our method for using these RPVs, I don't think you can do better than improving what they did by 1, but 1 is better than 0 or worse if you wanted the lower bound to be right. Okay, so actually this got us thinking about other things. I started to think about, could we play this game for higher Grassmanians? And I thought, everybody, it must be in the literature what the Morava K-theory of real Grassmanians are, and it turns out it isn't. So we started working backwards and trying to get at a non-equivariant result. So this is sort of fun. So everybody knows, the Morava, homology of Grassmanians is known, and it has total dimension equal to the number of cells it has, which is M choose D. And it has, classic presentation in terms of Stiefel-Whitney and dual Stiefel-Whitney classes, and then there's some ideal of relations, and it's rather elegant. It's not clear it's so easy to use all the time, but it's sort of elegant, and it's much studied too. So we started looking at this from the So for starters, we were able to show here's a theorem that is obvious if D was 1, if we're looking at RP, but it's not obvious what D is bigger. That the whole, the Atiyah-Hertzberg spectral sequence converging to the Morava K-theory collapses to a range bigger than you expect. You expect the first differential in when you compute Kn is this Qn guy, which is those jumps of like 2 to the n plus 1 dimensions, but whereas in GRD are 2 to the n plus 1, it's much bigger than, anyway, there are definitely chances for differentials to happen, but they don't. And so we get at this by just doing induction on n, and you choose a linear action of C2 on Rm, and you've sort of shown the theorem is true for n minus 1, and you get your fixed points are all in a situation you've already proved something about, and so we get a lower bound for the size from our theorem, and I'll give you a second, and the lower bound equals the number of cells, so it has is the upper bound. Yeah.
Collapse means collapse after the first material differential.
Actually, after no this one collapses at E2 after no differential. What this collapses, this is do I say something about this? No, I'm not yet. Okay. This means the E2, that means the cohomology. The cohomology, you're getting an associated gradient of Kn right away. So the E2 is the standard thing. It's the cohomology of the space with coefficients and just Kn star, which just looks like a copy of Z2 periodic, right? So it's just sort of extending the field, really. So it's looking a lot like mod 2 cohomology. That's what I'm saying. Yeah. So this is so we're getting a lower bound, and we have an upper bound by the number of cells. Can't be bigger than that. So that's sort of fun. Next page is going to get a little wonkier. Suppose you go beyond that dimension, and this is sort of, we have a lower bound for the size. It just looks like a blur of numbers, but you might notice it's a polynomial in, oh, that's right, we write this is 2 to the n plus 1, and then a little excess, and L is appearing there, and so it's sort of roughly a polynomial of degree d over 2. In M, kind of, for M large, okay. But this time we had to give it a C4 action, and a C2 wasn't rich enough, and we get a lower, and you take its fixed points, and you find you're in a situation where what you already proved on the previous slide applies to all the pieces, and it's C4, by the way, you we're talking now, if we're looking at fixed points, for GRD, you're looking at d-dimensional sub-representations. And so those could be like, you know, a 2-dimensional representation plus a 3-dimensional, I mean, you have sort of sums. This gives you smash products of things, of things. You also have this question, certain representations were really complex representations made real, so you start getting CPNs and things like this in your fixed point spaces. I guess you could have HPNs too if you, so you really do use all this good graduate algebra that you kind of should have studied. Anyway, so we have this bound, and it looks sort of random, but we think it's the right one because when we, if you Qn is this operation, Milner's operation. It's in the schema algebra. It's the first differential in the Hertzberg spectral sequence. It's also, if you like, atom spectral sequence. It's the E2 page of the atom spectral sequence is basically this number for computing. Say connective KM theory is roughly this thing as well. So it's the dimension, it's the kernel of Qn mod the image of Qn, and if it's an upper bound, it's part of a spectral sequence converging to what we want. And so if your upper bound hits this lower bound that we got before, then you will be done. And apparently my thumb wanted me to keep going, and so we think this is true. And you know, it's sort of weird. We have this fancy stuff with Morava K-theory, and we thought, oh, computing shouldn't be hard to compute these Milner primitives on this well-known ring, but it turns out it is hard to compute with it. But a lot of we mashed through it a proof when d equals 2 here, so 2 planes that the size of the Qn homology is exactly the number we wanted. When d is 2, there aren't a lot of terms there. It's like linear in L. L is basically M plus change. And Chris, actually, to make this conjecture something legitimate to conjecture, he got some sort of high power computing thing at Virginia and ran through some macho. So we have some tables in our paper that we checked. So you could actually check, you could have your computer, is the theorem true for this set of numbers? And you just tell the computer to work for a while and it tells you yes or no. So, and it always seems to be yes, so that's why we have it as a conjecture. So we have maybe a couple hundred other examples besides this general family, d equals 2. So it's sort of interesting. We are computing this stuff about the Morava K-theories of the Grassmanians, never thinking about interesting classes. So it's sort of a dumb proof. I mean, it's, we should be constructing some. It's interesting to think about. It's made me realize I don't know as much as I thought I did about the rational homology of real Grassmanians. They sort of have these Pontryagin classes, but you have this extra class that comes up once in a while, and then so it sort of follows that pattern. So that's another nice thing. I think part of our conjecture also ends up being that GRD RM is orientable with respect to all the Morava K-theories, if and only if M is even. So that's something you can see is true when ordinary, rationally is ordinary orientability. So it seems to be. So that's something interesting. So here are a couple of final remarks. If you want to work on something, here's some examples you might want to work on. There's a group of order 16, and we don't know whether its blue shift number is 2 or 3, and that's shifting down to the trivial group. So, just have to come up with a nice example out there. These dihedral groups, the difference between what we know, what's known, and the lower bound and upper bound gets arbitrarily large. So we haven't, I have no idea what to do there. So you need better sources of examples. We just use this one really sort of obvious thing or something of the projective spaces of linear representations, but maybe there's some other good examples out there. So, the upper bound maybe can be improved. This RD number, it's a rather weird function of G and H. One thing curious, if you fix G and let H vary, you might think it should be monotonic, but it's not. So that's a little weird. You can have a blue shift number down to the trivial group and it's strictly less than the blue shift number to something in between, which is a little weird. It sounds almost impossible, but it's true. In fact, it's so impossible that Chris found this example, and I said, this can't be right, and he explained it to me. And then 2 weeks later, of course, I'm going, this can't be right, and he explained it to me again, and about three times. So in our paper, we wrote down a lot of details there. So this is just so sort of a funny thing. Remember, it's this climbing up by cyclic groups, so you can sort of, the point is it's not monotonic because you could climb up through some other groups that you weren't dealing with. Anyway, there we are. So we have 2 papers up. One has been in, the first one has most of the stuff, and it's been sort of in referee purgatory, but I think any moment it may get accepted. But somehow this journal is really slow to make their decisions. And the second one has.
You're trying to pressure any editor who might be.
I did query them just before I came to see, well, can I help you with the comment? Anyway, we'll find out. Anyway, so hopefully. There you go. Pandemic refereeing. And the other one has been accepted already. It has this real Grassmanian stuff. Which is sort of fun. And anyway, there are problems there if somebody wants to think about good source of interesting classes in real Grassmanians. That would probably be a help. Anyway, there you are, and that's all I have.